Good afternoon, friends. Okay, so since the lectures for this course have finished, so we will start discussing a few concepts from the earlier part of the lectures, basically week 1 to 4, because they have actually some of the fundamental concepts of this course on robotics and control. So yeah, so briefly that would be the agenda for today. I will discuss two-hour manipulators, inverse kinematics and forward kinematics, and also control of manipulators in while following a trajectory basically. So first let's start the analysis of the kinematics of a two-hour manipulator, right? So our first agenda is right. So we have a two-hour manipulator. Basically, there are two links and there are two revolute joints, right, which are given by theta 1 and theta 2, and we have the frames assigned at each of the joints. So this x0 y0 frame is the base frame, basically this one. This is the frame at joint 1, and this is the end effector frame x2 and y2, and the link lengths are L1 and L2. So as you would remember, the process of computing the position of the end effector when the angles, that is theta 1 and theta 2, are known is forward kinematics, and when the position of the end effector is known and we have to compute the angles that this link should form in order to make sure that the end effector is at that position, so that is called inverse kinematics, right? So basically we want relation between the joint angles and the position of the end effector. So let's denote the position of the end effector as px and py, right? So quickly I would just write what I just said about forward and inverse kinematics. So forward kinematics, or FK, so let's say what's the input here? Input here is theta, right? And the output is the end effector position. Theta 1, 2, and end effector position px, py, and we have inverse kinematics. Let me draw this actually in the opposite direction. So here we input the end effector position, and we will like to know the joint angles, right? So why do we keep on coming back to this inverse kinematics problem? Because this is one of the fundamental requirements while while working with any robotic or device, right? Be it manipulators or as simple as this 2-hour manipulator or like humanoid robots, whatever. Because theta is the thing which you control using actuators. That's the thing the motors can control basically. And in order to do some task, you have to reach up to a certain position. So what links between this? So we definitely need a link between the position in the actual world and how much the angles should be in order to reach that position. So that's why inverse kinematics is used in every robotic application basically. It's running in the background in the code. So that's why it's a crucial concept to understand, right? Okay, so we will start. So you can maybe think that a obvious approach would be to write px and py in terms of L1, L2, theta 1 and theta 2, right? So we would get two equations, one an expression of px in terms of these quantities, another would be expression of py in terms of these quantities, and then there would be two equations, two variables. We can always find we can always solve the system of equations. So that's what we will do now, right? So I will also use the DH parameter approach so that uh, you get a revision of that also. So let's write the DH table for this. Right. So let's write the DH table. So DH parameters, as you would remember, they are the twist, the link length, the joint offset, and the joint angle. So basically, alpha I, that is the twist, then AI, that is the link length, then DI, the joint offset, and theta I, that is the joint angle. And there are two links only here. So yeah, so twist is 0 because everything is in all the rotation axes are parallel basically, and link lengths are L1 and L2. There is no joint offset also. So this is the one of the most simplest case, or the one of the most simple system of which you would write DH parameter, right? So theta 1 and theta 2, everything is in plane and all the joint axes are parallel to each other, right? So this is the DH table of this manipulator, right? And now you would recall that we had seen a big expression of the homogeneous transformation matrix, which basically gives the transformation from one frame to another frame, right? So this, lets me mark the frame also. So this is frame 0, this is frame 1, and this is frame 2, right? So the transformation matrix from I to I plus 1th frame. So basically, what do we do after writing DH parameters? We compute these transformation matrices from one frame to another frame, and finally we multiply all these transformation matrices to get the final transformation from the base frame to the end effector frame, right? So this matrix is a 4 cross 4 matrix. Let me just write it. So this is the general expression of the matrix. We will use the values of different parameters for this case to get the desired matrix. And yeah, so S means sine here and C means cosine. So in order to just keep things clear, I am writing like this. So as you would see, this 4 cross 4 homogeneous transformation matrix depends on the 4 DH parameters, theta, alpha, D and A, right? So now if we know the values of these DH parameters, so we can put the values and compute the matrix, the value of the actual matrix, right? So here we will first compute the transformation matrix from frame 0 to frame 1 and then from frame 1 to frame 2, right? So transformation matrix from 0 to 1, let me write it also, 0 to 1. Right. So for 0 to 1, we would put the values in the first row of the DH table. So alpha and D are 0 and A and theta are L1 and theta 1 respectively, right? So this D term would go to 0, these alpha terms would be 0, right? So just substitute the values from the first row of the DH table and you will get, you can also do this parallelly on your notebooks also, so that will give you a much better feel of the things if you wish. Right. So let me write a comment. Use first row from DH table. Now we will write the transformations from 1 to 2. 1 to 2. So now we will use parameters from the second row. Okay, so any doubts still here, then you can ask. Then, okay, so we proceed to the next step, which is, so basically now we have transformation from 0 to the first frame, then first frame to the second frame. So how do we compute the transformation from 0 to the second frame? We basically multiply them, right? So t0 to 2 is t2 1 t0 1, right? So now we will start doing the matrix multiplication. So finally what we get on multiplying is this matrix, right? So c theta 1 plus theta 2 minus s theta 1 plus theta 2 0 0 1 0 0. Okay, so this is the expression that we get for the transformation from the base frame, that is the 0th frame, to the end effector frame, that is the second frame, right? And now if you look at this matrix, so you can basically see two things. Let me just use a different color. Give me a minute. Right, sorry for that. Yeah, so you would see this part here, a 3 cross 3 matrix like this. So this 3 cross 3 matrix, this gives the orientation of the end effector, right? And this 3 cross 1 vector, this one, this gives the position of the end effector. So what is this? Orientation of the end effector, and this is position of the end effector, right? One thing that I wanted to confirm is the order of the multiplication here. So let me just see in the lectures. This should be in week 2. Oops, direct kinematics. Okay, so 0 to 1, 1 to 2, 2 to 3, 0 to 1, 1 to 2, 2 to 3. So we are basically post multiplying, right? 0 to 1, 1 to 2, 2 to 3. So yeah, there should be a change here. Please note that. So this would be first t 0 to 1 into t 1 to 2. Okay, you can verify this by doing the full matrix multiplication. Okay, so I need a next page. This is not good. What just happened? No. This is fine, this is fine, this is fine. Okay, so that was a very bad way to insert pages, but yeah, I had no other way. So let me just copy it here only. Okay, yeah, this looks good. Nice. Right, so we have the final transformation matrix from base frame to the end effector frame. This 3x3 matrix gives the orientation of the end effector, and this 3x1 vector gives the position of the end effector. We are concerned with the position of the end effector right now because we want to relate that quantity with the joint angles. Basically, that's what inverse kinematics is. So let me just go back to, yeah, so position of the end effector P, which the vector is given by this thing. So L1 cos theta 1 plus L2 cos theta 1 plus theta 2 and L1 sin theta 1 plus L2 sin theta 1 plus theta 2 and 0. Since it moves in the plane, the z coordinate is always 0, right? So now let's say we actually know the end effector position, right? Because in inverse kinematics we know the end effector position beforehand and want to compute the joint angles. So let's say the position is given by px and py, the x and y coordinates of the end effector. So we will get two equations, right? So px is equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2, right? And similarly in the y direction, py is L1 sin theta 1 plus L2 sin theta 1 plus theta 2, right? And we know px and py, and what do we want? So solve for theta 1 and theta 2. Okay, So now we have like done the hard part. Now it's just manipulation and solving these two equations to get theta 1 and theta 2, right? So yeah, let's do that. So first what should do is, let me just number these two equations. So this is 1 and this is 2, right? So px square plus py square is equal to, so this whole expression, if you square it, let's just write it. So it will be L1 square. Let me do one more, like just notationally simplify things. So c theta 1 I will write as c1, and cos of theta 1 plus theta 2, that I will write as c12, and similarly for sine also, right? So yeah, just quickly square it. So c1 square plus L2 square c12 square plus 2 L1 L2 c1 c12, right? And add py square in there. So py square is L1 square s1 square plus L2 square s12 square plus 2 L1 L2 s1 s12, right? Now this L1 c1 square and L1 s1 square, and this L2 c12 square and L2 s12 square. So we use the identity cos theta square plus cos square theta plus sin square theta is equal to 1. So these two terms can be written as L1 square, and similarly other two terms can be written as L2 square, right? Now for this L1 L2 term, so what is this? This is 2 L1 L2 c1 12 plus s1 12. But this is basically the formula of cos theta 1 plus theta 2, right? Sorry, cos theta 1 minus theta 2, right? So, and here, so what it will be? It will be basically, this is basically, if I'm writing it back again in a clearer way, so cos theta 1 so cos theta 1 plus theta 2 plus sin theta 1 and sin theta 1 plus theta 2. So this is basically cos of theta 1 plus theta 2 minus theta 1, right? Cos A, this is formula of cos A minus B, right? Where A is theta 1 plus theta 2 and B is theta 1. So finally what we will get here, so this theta 1 and theta 1 goes, so finally just theta 2 remains. So what will be the expression? L1 square plus L2 square plus 2 L1 L2 cos theta 2, right? So from here you can see that so the left hand side we know L1 L2 we know, so the only unknown is in this equation is cos theta 2, and thus we have the expression for our first angle. So cos theta 2 is cos theta 2 is uh, so the expression for the first joint angle is cos theta 2 is equal to px square plus py square minus L1 square minus L2 square by 2 L1 L2, right? Okay, so from here you can get theta 2, basically sine theta 2 would be plus minus under root 1 minus cos square theta 2. Okay, so we have got the first angle. Now for the second angle we would need some more manipulation. So basically we multiply the px equation with cos theta 1, right? Multiply px with cos theta 1 and multiply py with sin theta 1, right? This equation, multiply px by cos theta 1, multiply py with sin theta 1. Okay, so what we get, if you do that, you get L1 plus L2 cos theta 2, and similarly if you multiply px with minus of sin theta 1 and py with cos theta 1, you would get L2 sine theta 2. Now again, what we do, we multiply these two equations with px and py respectively, right? So again, upon doing this, we get cos theta 1 is equal to px so cos theta 1 is px L1 plus L2 cos theta 2 plus py L2 sin theta 2 by px square plus py square. Okay, so now you have the second angle also. Okay, so you have cos theta 1. Oh shit, wait. What the, oh man, things have got erased. What was here? Here was orientation of the end effector. Yeah, now it's fine. So again, let me just see. We did the DH table, we calculated the transformation matrices, the final transformation matrix, we got the position of the end effector, we know the actual position of the end effector, we formed two equations from which we solved for theta 1 and theta 2, we got the expression for cos theta 1 and cos theta 2, right? So this is the analytical solution. Okay, just wait a second. Now let's move on to a different topic, right, which I would like to discuss today. So this is about the control of manipulators, right? So basically, we have generated a trajectory and we would like to follow that trajectory as close as possible. So how to formulate a control law so that our manipulator follows a given trajectory? So we will start with the analysis of second order systems. So just a little bit I would like to give little bit more theoretical background before we go into the actual trajectory tracking of by manipulators. So first we'll start by analyzing second order systems. And as soon as you hear this term second order system, the first thing in a mechanical perspective, the first thing that comes to the mind is a spring mass damper system. What does we have? Spring mass damper, right? And you know the very common equation, mx double dot plus bx dot plus kx is equal to 0. This is the unforced, right? So this is the damping term and this is the spring term. So let me just draw figure quickly. So we have the mass here and we have the spring and we have the damper, right? So this is K and this is B, this is M, and we are measuring X. All right. So this equation mx double dot plus bx dot plus kx, this equation, how to find solutions for this equation, because basically that's what we are interested in, right? How the x evolves given these three parameters m, b and k. So basically we assume that let x be of the type, so xt, let it be of the type e to the power s t, basically. So x dot will be s e to the power st, and x double dot would be, if you differentiate it once more, you would get x s square e to the power st, right? So substituting the value of x dot and x double dot in the original equation, we get what we call as the characteristic equation. And that is m s square plus bs plus k equal to 0, right? Now this is a very familiar looking quadratic equation, right? And we can always find certain certain conditions on these m, b and k such that it changes how many roots does this quadratic equation have, basically, right? So you know the formula for finding roots of a quadratic equation, minus b plus minus under root b square minus 4ac by 2a. So just applying that, we get the value of s, so that will be minus b by 2m plus minus under root b square minus 4mk by 2m, right? And these are what are called as poles, more formally poles. or roots. Now, depending on what this quantity is, b square minus 4mk, the discriminant of the equation, right? The d b square minus 4mk. Depending on whether this is positive, negative, or 0, we have three cases, right? So, case 1, d is greater than 0, right? So, when d is greater than 0, then we have two distinct real roots. Right, so two distinct real roots. This is the case which we call as overdamped. And in this case, there are no oscillations. So basically this is this is supposed to be an oscillatory system, right? You would expect some oscillatory response here, but in case of overdamping, there is no oscillations. Then there is a second case where d is less than 0. Then there are complex roots, right? And here we have oscillations, periodic oscillations. And the third case, that is the boundary case, that d is equal to 0. This is called as critically damped. So just enough damping that there are no oscillations, right? So in most of the cases of control, ideally we would like to be critically damped. This is our aim, basically. We would like our systems to be critically damped in most of the cases, if not all, right? So, and in this case, b square minus 4mk is equal to 0, right? So b is equal to 2 under root mk. Okay, so for this value of b, the system is critically damped. Okay, now the response is basically given by so I should write here s1 comma 2, right? So the response basically is given by c1 e to the power s1 t plus c2 e to the power s2 t. Okay, now so this is very basic about second order system, right? When the second order system is critically damped, when this condition holds, basically, right? Now let's say we try to control this spring mass system, control of second order systems, right? So a very common or the most basic control law looks something like this. There's something wrong with my no man no. What's happening? Okay, so the most basic form of the control is mx double dot plus px dot plus kx is equal to f, right? So let's say if we apply we have an actuator which applies this force kp times x minus kv times x dot, right? So what does this control law will do? It if x deviates from the desired position, it will try to bring it back. So basically this control law maintains a position. This is to maintain a given position of the block, right? We are not yet tracking a trajectory. We just, let's say we want to keep the block at x is equal to 2. So this control law will try to just maintain the position of the block at x equal to 2, right? So if we put the expression of f in the equation, so this is mx double dot plus px dot plus kx is equal to minus kpx minus kv x dot, right? So this becomes mx double dot plus b plus kv x dot plus k plus kp x equal to 0, and let's denote this as p dash and this as k dash, right? So if we want our system to be critically damped, so for critical damping CD, this is CD critical damped. So for critically damped system, we have b dash is equal to 2 under root k dash m, right? This we would follow. Okay, so what we have just seen, we saw how to maintain the position of the block using a control law. So basically this force will be provided by an actuator which will keep the block at a given position. Now we come on to something called as control partitioning. So control partitioning. conditioning. Okay, so what we do, we had that equation mx double dot plus px dot plus kx equals f, right? Now let's represent f as alpha times f dash plus beta, right? So now we would design, so alpha and beta are some parameters which we can choose, right? So we would choose alpha and beta as such that this equation, the first equation, when we put alpha f dash plus beta here, this equation reduces to a equation of a unit mass, right? And what's the advantage of using that is we will see, right? So we will choose alpha is equal to m and beta is equal to bx dot plus kx, right? So this is 1. So in 1, if we substitute, so what will you get? Mx double dot plus px dot plus kx is equal to f, which is alpha f dash plus beta, and alpha is m, so m f dash plus beta is px dot plus kx, right? So what are we getting from here? This x double dot is equal to f dash, right? So this is what I was talking about. This is the, and what is this? This just represents equation for unit mass, right? This represents equation of a unit mass. Now let's choose f dash as, so now we have to choose f dash, like how do we compute f dash basically? So again, as before, let's choose f dash as kp times x minus kv times x dot, right? And since now f dash is equal to x double dot in our system, so x double dot is equal to minus kpx minus kvx dot, right? So this is the system. kv, I should write kv here, but it's fine. So this is the simplified, like, second order system. And if we want x to be critically damped, so you see that we have eliminated all the other parameters m, b and k. We have freed the model from those parameters, and now we just have two parameters here, kp and kv. And for critical damping, what do we have? B is equal to 2 times under root km. So B here is kV, right? 2 times under root kp, right? So this is the relationship basically between the k, these two gains. These are gain values. So this is the relation between the proportional gain and the velocity derivative gain for critical damping. Okay, and now we can come on to trajectory tracking. Right, so you have also seen how to generate a trajectory, and let's say we have a trajectory. So what are the things that we have? We have the desired position, desired velocities, and desired accelerations. Yeah, this is for the end effector. For the end effector, right? So we define the error as usual, xd desired minus the actual, right? This is actual, this is desired. Desired or reference, these are the terms which we use, and this is actual. This is the basically error, and our goal is to design a control law such that the error goes to 0, right? So basically what we would do, we would derive what we call as error dynamics and make sure that the error dynamics is critically damped, right? So here we select f dash as xt double dot plus kv e dot plus kp e, right? So, and what is f double dash? Sorry, f dash. We again follow this unit mass thing. So f dash is x double dot, right? So x double dot is equal to x double dot desired plus kv e dot plus kp e. And what is e dot? E dot is xt dot minus x dot, right? And again, if we take bring x dot this side to the right hand side, so what we will get? We will get e double dot plus kv e dot plus kp e is equal to 0. Right, and this is what I was talking about, the error dynamics. And this has to be, we can make this overdamped also, but generally has at least we have to keep it critically damped, right? So again we use the critical damping relation, right? And we get kv is equal to twice of under root kp. So basically, if we select kv and kp such that they satisfy this relationship, then we will track our trajectory as closely as possible, right? So any questions on either the control part or the inverse kinematics part? Any questions from you guys? Okay, so apart from this also, like uh, any topics which you would like to be discussed in the next week's discussion hour. So if there are any specific topics, then you can let me know. Otherwise, yeah, I will just again bring up some useful topics and we will go through them. So if there are no questions, then I think we can wrap up for today. That's what I had from my side. So okay guys, so we will meet again next week for the final discussion hour of this course. So see you then.
Thank you, sir.
Thanks, Josh.